Hello everyone. So welcome over to my lab, or my desk. So what I want to go ahead and cover today is kind of do an introduction to this NI MyDAQ. And the NI is for the company that produces it, National Instruments. And the DAQ part stands for data acquisition. So the whole idea behind this guy is that there's a few key pieces of test equipment that we want to have whenever we're working with electronics or looking at signals for an embedded system or FPGA, etc. And so the MyDAQ actually has a lot of tools in one. And so I want to go ahead and do this introduction to it. Let me go ahead and switch some of my cameras up over here. And I'll zoom in on this guy. So when you go ahead and get that box, you're going to open that up and you're going to find this tool over here. And as I said, this is going to serve as a bunch of different instruments that we can use for taking measurements and looking at our signals and producing signals and also acting like our benchtop power supply. So let me go ahead and cover the basic tools that we're going to use this as. Okay, so first up, for any circuit that we're going to test, let's go ahead and draw a black box just to represent some circuit. And normally when you have some circuit that we're going to be testing or verifying, we would call it a DUT. DUT just stands for device under test. And so generally speaking, we want to apply some input signal and then we get something out of this. Generally speaking, another output signal, maybe 2 or 3 or more. And so we're going to need to generate some type of stimulus for our circuit. And to do this, normally we use something called a function generator. And now, in order to see what comes out of it, we're going to need to go ahead and use something to view the signal of interest. And that tool is an oscilloscope. So the function generator would be producing the signals. And the oscilloscope would be viewing the result. And an oscilloscope has the ability to view voltage with respect to time. And so if you've been using LT Spice, you know exactly what you're looking at. You're looking at the voltage with respect to time that's being produced by our device under test. Or even our oscilloscope has 2 channels. And since the function generator cannot view the signal that it's generating, like oftentimes we take one channel and we also use it to view our input at the same time. Okay, so in this case we may have channel 1, viewing the input and channel 2 similarly would be viewing the output. And then you can compare the input and the output, and you can see exactly what your device under test does. Okay, and so I'll be running through an example with this. Now, when you're looking at these tools, if I switch over views, a function generator, I actually have a couple of them over here. I have one up here, and I have another one down here. And for the oscilloscope, similarly, I have one up here, which is a digital, and I have an analog scope down here that I use. An analog scope can be very useful, in some cases better than a digital oscilloscope. So I tend to keep both on my desk. Now, that being said, we're doing all of this at home or maybe in another lab. And that test equipment does cost quite a bit. You know, my oscilloscopes probably total about $1,000, and my function generators a few hundred spent in function generators. However, what is very cool is that this device can serve as both of those. So it has the capability of producing signals as well as viewing two channels at the same time. So we have a function generator in here. We also have a two-channel oscilloscope. Also, this will also provide some voltages for us to use for our circuits. So we can also power our circuits off of this device. So this is also acting as a benchtop power supply. Now, the voltages that we have from this benchtop power supply is not nearly as versatile as, say, a standard benchtop power supply. And I have covered benchtop power supplies before, and I do have a couple on my bench as well that I'm pointing to right here. But the MyDAQ will give us the basics of what we need. So we're going to get a plus 15 volts from it. We can also get a minus 15 volts fixed from this as well, and a 5 volts. And so we obviously are going to have a ground rail for our power supplies. All of these voltages are in reference to the ground of the device. And we also get 5 volts out of it, positive 15 and minus 15. And this will actually work quite well for us. There's often times where we do need a negative voltage supply, and we can get one out of this MyDAQ. Now, I will say the MyDAQ is professional enough for us, but it doesn't have that much current sourcing ability. You can't get, say half an amp or a full amp from this device for any of these power rails, but it is sufficient. I believe like 100 milliamps you can get for each one of these voltages, and that is more than enough for any of the experiments that we're doing. Similarly, the two-channel oscilloscope, it's not as good as, say, a benchtop unit or a professional oscilloscope, and it's just limited in the frequencies that it can view. I believe the bandwidth which is kind of one of those numbers that you generally care about when you're looking at an oscilloscope. The bandwidth for the MyDAQ is 400 kilohertz, so you're not going to be able to view very fast signals, but nevertheless, the slow signals that we're going to be working with and the circuits that we would be using this with, this is going to be more than adequate. And I think it's a tremendous value for $200 for all of this test equipment in one, and it is a USB device, so it's easy to carry and take with us anywhere that we want to go ahead and do some work. All right, so let's go ahead and let's go over the signals that we're going to want coming out of here. So let me adjust the focus on this. Okay, I believe that's a little better. In fact, let me get something to prop this up on. Okay, so I'm looking from left to right. And over here we have one connector for plus 15 volts. That's for our power supply. We also have the next one over, which is for minus 15 volts. And that's also written at the top right here. And so that's the second connection. And then we have 2 pins for ground. And they just put an A there to signify analog ground as opposed to a digital ground. They're all going to be the same for us. Analog ground, these two. And then we have A0, or I should say AO for analog out. And we have 2 channels. So this is our output. This is our function generator. We're going to take it from 0 or 1. And so they give us 2 channels for that. And let me actually rephrase that. Plus 15, minus 15. There's only one connection here for the analog ground. And then channel 0 and channel 1. And then we have another analog ground. And these are our outputs. We also have our analog input. This is for the oscilloscope. And for the oscilloscope, each channel has a positive and a minus. So whenever you're viewing a voltage or whenever you're measuring a voltage, you're going to be measuring it in reference to something, right? I don't have a voltage at only one point. I have a voltage between a point and something else. So we're going to need a minus and a positive for each one of our channels. And so we have a channel 0 with a positive and minus, and we have a channel 1 positive and minus as well. And so let's only worry about the function generator and oscilloscope. There's a lot more functionality that you can get out of this device. It can also behave like a logic analyzer and quite a few other functions. But let's just focus with the oscilloscope and the function generator for now. So what I'm going to go ahead and do is I'm going to hook up some wires just like you would on your bench. Let me go ahead and fix the focus again. There we go. Okay, now each one of these connections comes out to a screw terminal. And so there's a screwdriver that comes with it, just the right size. It is perfect to fit in there. And we can go ahead and unscrew all of the signals that we are going to be interested in. So I'm going to make sure that all of these are loose. And we're going to connect the bare minimum to this guy in order to demonstrate its functionality. Okay, we're going to need plus 15 volts. So I'm going to stick one of these prototyping wires, one of these breadboard wires, into the first terminal that says plus 15. And then I'm going to go ahead and tighten that down. Now, for now, I'm going to skip the minus 15. I'm not going to be using that for this first demo. And the next one is going to be a ground. I'm going to connect a black wire for that one. So I skipped the minus 15. I'm now going into the third position, which is called a ground. Okay. And next up is going to be my analog output. So I'm going to connect this analog output 0. There's a 0 and a 1 because we do have two channels that come out from this function generator, but we're just going to be using one for now. So I'm going to use a white wire for that one. We're going to skip the analog output 1. We're going to skip the A ground for the analog input. And we have a 0 plus and a 0 minus. So for the 0 plus, I'm going to go into a a yellow wire for now. This is on 0 plus of A in. And just make sure that those are secure once you tighten that down. You don't need to tighten it very much. You don't want to break these connectors. So just give them a little snug, not too much. Don't crank down on those. And we're also going to need the channel 0 minus, and I'm going to use a green wire for that one. Okay, again, just a little snug on that. And we're going to go ahead and just demonstrate functionality with only these connections. Plus 15, ground, our signal out from our function generator, our oscilloscope input positive, and our oscilloscope input minus for channel 1. Okay, and for these tests, I'm going to go ahead and I'm going to connect these to breadboard just for now. And I've already set up a very simple circuit, but even before the simplest circuit that I would test, I always like to verify the functionality of my function generator and my oscilloscope. So for now, I'm going to move these over. And I'm going to set up my breadboard as I typically do. So over here you can see I have a minus rail that goes all the way across the board. I have a positive rail going all the way across the board below that. And then I've jumpered the minus to the minus down here so that I have access to ground on both sides of my board to make it very easy for me to place components, whether I need ground up here or ground down there. And the same thing for my positive rail. So what I'm going to do is I'm going to take my plus 15 and I'm going to attach that to my positive rail. And I'm going to do this down here just to keep some of these wires out of the way of my function generator wires and my oscilloscope wiring. And now I'm going to take ground and I'm going to do the same thing. I'm going to attach it down here to the minus rail. And now I'm left with a few wires. So my signal for the function generator, I'm just going to place it in an unused group of 5 for right now. And I'm going to take my ground of my oscilloscope. So that green wire that I connected to channel 0 minus. And I'm going to attach that in another unused group of 5. And I'm going to do the same thing with my oscilloscope channel 1 positive. Okay, so right now I just have power to my board, and all the other inputs and outputs are just in their own connectors over there. Now at this point we can go ahead and fire up the MyDAQ and launch the software, see what that looks like. Now when we go ahead and plug it in after you've installed the software, and there's a link on my page for how to do the software, once we plug it into our computer, it's going to actually automatically start up the software, and we should see that. So what I'm going to do over here is take the supplied USB-B cable that came with it, plug that into my computer after the software has been installed, and now I'm just going to go ahead and plug it in. And it would probably help if I also had it plugged into my computer myself. Okay, so now my computer has given me the ceremonial ding of the USB device connected, and it started up the software. So let me go ahead and switch my view over to my desktop. Okay, so it said device detected NI MyDAQ. And one of the things to know, something that I've noticed, is that when you first connect it, the software automatically runs, but it does take a few seconds before a couple of the other tools come up. So you may notice there's going to be a little bit of a delay, and it's about 2-3 seconds. You plug it in and you're like, oh, I got the screen, and then it doesn't have the software of interest loaded in there yet. Give it a few seconds, it will pop up. Okay, now the first thing it says test this device. I'm not going to bother. We'll test it with the actual software. Next, configure and test this device. Not going to worry about that either. View online device documentation. View device pinouts. And what we care about, launch instruments and apps for this device. Hit go next to launch instruments and apps for this device. Okay, very cool. So now we have some software, and we got a lot of functionality that we can get out of this little guy. We have an arbitrary waveform generator, a Bode analyzer, a digital reader, digital writer, digital multimeter, dynamic signal analyzer, function generator, oscilloscope, 8-channel oscilloscope, audio equalizer, data logger, DC level octave analyzer. Okay, so let's launch the function generator. All right, when you do that, you're going to get a window, and you can move this around and move it around your screen, place it wherever is convenient. And you can see we have the ability to generate a sine wave, a triangle, a square wave, adjust the frequency, adjust the amplitude, adjust the DC offset, all of that fun stuff that we want from a function generator. And you can see over here the instrument control. The device has already been selected to our MyDAQ, and the signal route, you can select whether you want this on channel 0 of our function generator or channel 1. Now our function generator, we did have 2 signals we could output on. However, we only connected our wire to A0. So let's keep it on A0, or I should say analog out A0. And we'll just leave that there. Don't worry about running it yet. The next tool that we need to fire up is the oscilloscope. So go ahead, click on oscilloscope, and now we have a nice window to view our waveform with. Okay. And let's see. I can't actually resize. Let me see if Let me resize my desktop and maybe. That'll give us a little better zoom on what's going on here. There, I'll run this like this. Okay. And I'm cutting off just a tad bit of the there we go. Okay. Now, if we just turn our function generator on, well, we're not going to see anything. We will just be supposedly putting out some output signal. And similarly, if we turn on our oscilloscope right now, we're not going to see anything either because, well, it's not looking at anything. So let's go ahead and switch over to this view. And let's do something here on my breadboard. Let's take the function generator output, my white wire, and we're going to connect that to the oscilloscope input over here on my yellow wire. So remember, my yellow wire is analog in positive. Now green, remember I have to measure a voltage with respect to something. So I'm going to connect this to ground since that's the 0 volt reference for all of our circuits. And ground is going back to the MyDAQ through this black wire. Okay? So now hopefully if you can see, I have the function generator output connected to the oscilloscope input. Now let me go ahead and switch back over. And now let's turn this on. I'm going to set my frequency to be 1 kilohertz. 1 kilohertz is what we're going to be using in this next lab. So let's go ahead and change this. Oh, that's going to take forever if I use this box. I'm going to highlight the whole thing and I'm going to type 1000. Okay, that's 1K. And when I hit enter after I typed in 1000, it took that setting, and if you notice, the dial moved over here. We're interested in producing a sine wave, so I'm not going to worry about generating a triangle or a square wave for that right now. And if you notice, you can hover over any of these and it'll give you a little tooltip that tells you what it is. We're going to generate sine wave at 1 kilohertz, and we're going to leave this at 1 volt peak to peak right now. Okay, so I can adjust my amplitude and I can change what that voltage out is. And if you notice, the units that are next to that say VPP. That's voltage peak to peak. Okay, so that means our peak voltage is 0.5 volts. So it should go up half a volt and then come down to a minus half volt. Okay, now our DC offset, this is how far away the center of that sine wave is from our 0 on the y-axis. And we're going to leave that at 0 volts. We want it centered at ground. So this is going to go up to positive 0.5 and down to minus 0.5. And at least that's what I think by these settings right now. So I'm going to go ahead, hit run, and I see nothing happening. Okay. Supposedly I'm putting out this signal on the function generator right now. However, I don't have my oscilloscope running yet. So we're going to also need to hit run on our oscilloscope screen or window over here. So without changing any of the defaults are already set for our analog in channel 0. That's the source up here. It is enabled. The checkbox is checked. I'm going to leave the scale to be, by default, it's set at 1 volt. Our time base by default is set at 5 milliseconds per division. I'm going to leave that. And our acquisition mode is run continuously, and the device has already been automatically set. So let's go ahead and hit run. Ooh, cool. All right. I got something. This is good. And if I go back to my board, I'm going to disconnect the function generator, that white wire. I'm going to unplug it. Oh, sure enough, we lost our signal. We're still picking up something, but that's coming over on the ground, and that's actually just noise, because both wires from our analog input need to be connected in order to see anything. So again, I'll plug that back together. So looks again like we are reading the output from that function generator. Okay, so keep track be aware these are acting like two fundamentally different instruments, even though they're coming from the same device, even though we're running the same software. Each window, one is a function generator that's generating an output, the other one is an oscilloscope that is viewing the result of that. And unless those wires are connected to each other, we're not going to measure anything. Okay, so now this is quite small as far as the vertical axis is concerned. So I'm going to change the scale, my volts per division. Right now it's set at 1 volt per division. And so if you notice, each one of these squares represents 1 division, both vertically and horizontally. But when you're talking about the scale, the voltage is shown with respect to time. It's time along our x-axis, voltage along our y-axis. So if I go ahead and increase, if you see, now I have it set at 500 millivolts per division. Well, notice our output is outputting 0.5 volts peak. So it's going up to positive 0.5. It's going down to minus 0.5. Well, look at what I have set up over here. I'm showing 500 millivolts, or half a volt per division. So no surprise, our signal is going up 1 square, as it should. Okay, if I go ahead and change the volts per division again, let's go ahead and let's make this 100 millivolts per division. Actually, let's go there. Let's do 200 millivolts per division. So notice on our screen, it's a little hard to see, but from the center axis, we're going up 1 square, 2 square, and a half square. Okay, so 2.5 divisions. 2.5 divisions. Well, each division is representative of 200 millivolts. So you're going up, one division would be 200, another division would be 400, and half of a 200 millivolt division is another 100. That takes us to 500 millivolts. Okay? So all I'm doing is zooming in and out along the vertical axis on our oscilloscope. I'm not changing the output level from our function generator. Our function generator is still producing a 0.5 volt peak signal. It's going up to positive 0.5. It's going down to minus 0.5. All I'm doing is zooming in and out with my oscilloscope. Think of your oscilloscope as a microscope for signals, and you can increase that magnification, you can decrease that magnification. Okay, so that takes care of our vertical axis. Anytime you want to see more or less of your signal, you can change that volts per division And you can also use those divisions to take measurements. Over here, I now have it set at 100 millivolts per division. So from that center axis, you're going up 100, 200, 300, 400, and the peak goes to 500 millivolts, or the 5th division. Okay, so let me go ahead and take this back down to 200 millivolts per division, since that gives me a pretty good view of the output from my function generator. Now, if you notice, it's sliding back and forth, okay? Now, the reason for that has to do with what we refer to as triggering. Your oscilloscope has a trigger, and that trigger is what tells the oscilloscope to place the same rising edge of your signal in the same spot over and over and over again. And so this is going to keep track of the signal and prevent it from just sliding back and forth across the oscilloscope screen. So I'm going to go over here, and I'm going to change my trigger type to be edge, okay? So we're going to be triggering on either the rising edge or the falling edge of this sine wave. Okay, and notice already by default, that has prevented our signal from sliding back and forth. Okay, now let's go ahead and kind of talk a little bit about the horizontal axis. So our horizontal axis is indicative of time. And again, I can do that same thing of zooming in or out. So let's go and change the time base over here. Right now it's set at 5 milliseconds per division. Let me increase that to, or let me decrease that to 2 milliseconds per division. And notice now we can see a little more of, we see fewer cycles, but we can get a little better view of the individual cycles. I'm going to take this down to 1 millisecond per division. Let's go 500 microseconds per division. And now you can see we got a pretty nice view of our waveform. And if I start from the left side over here, if I look at what one cycle is, here's one cycle. Okay, right here where we cross that x-axis again is one cycle, 2 cycle, 3 cycle, 4 cycle, and 5 cycle. So I'm seeing 5 cycles of my sine wave that I'm producing from my function generator, and I'm viewing that on my oscilloscope. Okay. Now we can see clearly that the oscilloscope is triggering on that rising edge. It's right there in the center. If I change my slope of the trigger, notice now I've changed it to a negative edge. So now this is triggering on the negative edge. It places the negative edge of our repetitive signal right in the center of the screen. Okay, I'm going to go back over to positive edge. Okay. Now, you can also change the horizontal position. And if you notice, the red line is moving left and right. So that's changing where my trigger point is on my screen. Okay, that's the horizontal position. I'm going to put that back at the default of 50% right in the center. Okay, I won't worry about changing that too much. Let's also talk about the trigger level. So for the trigger to work, for the oscilloscope to actually trigger on the rising edge of our signal, it needs to know at what voltage level that triggering is going to occur. Right now, if you look at the vertical axis, we're going up 2.5 divisions. We're going up to 500 millivolts. So if I take my trigger, and if I set my trigger level to be 0.4 volts, notice I'm now triggering up here. In fact, the crosshairs moved up to signify that. And so we're still triggering. In fact, I can go up to 0.45. Notice that crosshair moved up yet again. So now it's triggering on this tiny portion of the top of our signal. And again, let's take this to 0.49. Let's see, we are still triggering at 0.49. However, once we get outside of the range of our signal, once we exceed that voltage range, the oscilloscope's going to not find a signal there. It can't trigger at a voltage that's not at that level. Our function generator is producing 0.5 volts peak. So if I go ahead and take this to something like 0.6, notice it's now saying waiting for trigger. Okay. So waiting for trigger. There is no signal happening at 0.6 volts. It's all at 0.5 volts. So I'm going to take my trigger level back down to 0. And I'm going to leave that there since we're going to be working with a signal that crosses the 0 axis and has no DC offset. This is a pretty good place to have our trigger set at. Now let's go ahead, let's talk a little bit about the time base. The time base works very similarly to the vertical, the volts per division, the scale along the vertical axis, in that you can use those squares in order to figure out the frequency or the period of your signal. So let's go ahead, let's take a measurement here. My signal, let's start at where it crosses the 0 axis, right here in the center, and let's see how long does it take to complete one full cycle. So a cycle always starts at one point and it finishes when it's back at that same point. So I'm just going to use our 0 crossing as our indication for where the cycle repeats. So over here it starts, and over here is where it starts to repeat. So this is one cycle across here. And if you notice, 1 square, 2 squares. Okay, so that's 2 divisions. I'm going to write down 2 divisions. And notice that each division is representative of 500 microseconds. I'm going to write down 500 microseconds as well. Okay, so our period is 2 divisions with each division representing 500 microseconds. So 500 microseconds times 2 is going to be 1 millisecond. That is the period. So if we want to go ahead and calculate the frequency, let me jump back over to my whiteboard. I already wrote it down. 2 divisions at 500 microseconds was the period of the waveform that we were viewing on the oscilloscope. So I wrote down periods equal to 1 millisecond, and frequency is equal to 1 over the period. Well, what's 1 over 1 millisecond, or 1 divided by 0.001? It's 1 kilohertz. Okay, so no surprise because we set our function generator at 1 kilohertz. So if I go back over to my desktop view, you can see I set the frequency at 1 kilohertz. And in fact, you can also see on the oscilloscope that's viewing the waveform, you can see that it's measuring 1 kilohertz. In fact, it gives us the frequency down here. So the tool is calculating the frequency for us based off of where our signal repeats. Now, if I go ahead and let's say we double this frequency, I'm going to go from 1 kilohertz, I'm going to change this to 2 kilohertz. Okay, I guess I got to type it in. 2K. Enter. All right. Notice now that our signal, one cycle takes 1 square instead of 2 squares. That makes a lot of sense. Our frequency just went up to 2 kilohertz, and that means the period went to, what is the period over here? Well, it is 500 microseconds per division. 1 cycle is 1 division, so 500 microseconds. Okay, so now we can go ahead and we can start playing around with our function generator. We can see what the output's going to look like on our oscilloscope. So first off, let's go ahead and instead of a 0.5 volt peak signal, let's change that to 1 volt peak signal. Okay. Now, our amplitude on the function generator is listed as peak to peak. So if I want a 1 volt peak signal, that means I'm going to need a 2 volt peak to peak signal. So I'm going to change that 1 to 2. Notice now our signal amplitude as viewed on the function generator just went up. And in fact, I'm going to crank down the frequency back to 1K. Just so we can see this a little better. And do I have the ability to change the color of my, I don't think I do. I wish I could change it to yellow. Oh, maybe graph properties. Background color, channel, oh, here we go. Channel 0 and channel 1. Okay, I'm going to actually change channel 0 to be yellow, orange. There we go. I don't know how much better that is. Let's lower the frequency again. Let's do half of this. Let's go to 500 hertz. Okay. I like yellow and blue because those are the colors used by my oscilloscope on my bench. Okay. So now let's go ahead and let's see. We went to 2 volts peak to peak, which means we're going up to 1 volt. Now each division is representative of 200 millivolts, so we're going 200, 400, 600, 800, and 1000 millivolts, which is 1 volt. Okay, so our function generator and our oscilloscope are working perfectly. Now, I always do a test like this before I bother connecting components to this. The reason is I want to make sure that my function generator is working, that I'm getting a signal out of it, and I want to make sure that my oscilloscope is working and that it can view a signal before I bother connecting anything. Okay? Now, I recommend this. And I always recommend testing each thing. The last thing I want is a bunch of variables that I don't know if they're working. This is why a lot of students, go, it doesn't work. I don't know what. I'm like, I don't know what either. What about the project is not working? Well, I don't know, the whole thing. And you go, come on, what? Didn't you test out individual pieces? Always get in the habit of testing and verifying the individual components of your entire system before you bother connecting the whole thing together. You're just going to waste your time if you hook everything up and you expect it to work. One thing I can guarantee you is nothing will ever work the first time. And even after you find one problem and you fix that one problem, it still is not going to work. You probably have about 10 things that are wrong when the whole system's not working. Whether this is an embedded project, whether this is a circuit, whether this is an FPGA project, you can't throw the whole thing together, expect the whole thing to work. So why don't you save your time make your headaches smaller and test the individual pieces before you put it together. Right now, I'm confident that my function generator is working. Right now, I'm confident that my oscilloscope is working. Now is when I'm going to go ahead and hook up a circuit to test. Now, the circuit that I'm going to test, I'm going to go ahead and test that very simple series diode clipper circuit. And to do that test, let's go ahead and let's increase our function generator to, let's do 5 volts. Let's see. I want to be well above the forward voltage. So let's pick, we could do 3 volts. Yeah, let's do 3 volts. So I'm going to do 6 volts peak to peak. Notice now that it's just gone off of my screen. So I'm going to change the volts per division so that my waveform is nicely there. It's at 1 volt per division. Sure enough, I'm going up 1 division, 2 division, 3 divisions. Okay. Similarly, I'm going down 1, 2, 3 divisions. And my frequency is 500 hertz. I'm just going to leave it at 500 hertz. No, for this test, there's no reason to go with anything. It doesn't really matter. So let's go back over to the whiteboard and let's hook up our test circuit. Series diode clipper. Notice I've placed my rectifier diode here. Let me go ahead and bend this out so it's a little easier to see. And I don't have anything connected to it yet. And it's just going through a 1K resistor, okay? You definitely want to have some current limiting resistor on here. I believe 1K will work just fine for these purposes. Now, I'm going to take my input. And by input, I mean, output. I'm going to take my function generator output, and I'm going to connect that to the input of my circuit. So this is just like lab 2 or 3. And I'm going to take my channel 0 of my oscilloscope, and I'm going to hook that up to the same point, because I want to view the input and the output. Wait a second, I'm going to need 2 channels for this. Okay. Now, I really do need to have ground connected to my circuit. So what I'm going to do, I'm going to place the bottom of my resistor into the same ground that's connected to our black wire, which goes to our ground of our MyDAQ. Okay. So now at this point, if I jump back, we have our signal being applied, and we're measuring the input of our circuit. So this is our applied test signal. And don't ask me, I don't have an explanation for this yet. First time I've seen it. I'm sure there's a very good reason for it. Let's go ahead and now let's turn on channel 2 for our oscilloscope. Now, to get access to channel 2, I'm going to have to go into those little screw terminals. And if you notice, I have a 1 plus and I have a 1 minus under my analog input. So I'm going to use another 2 wires for this. I'm going to do a green wire for the minus. And I wouldn't mind if I had a blue wire for my channel 2. So I'm going to look and see if I have a blue wire. Okay, I do. However, it is fairly short. So I'm going to connect that blue wire over to 1 plus. Now my minus of channel 2, I'm going to have to also have that connected to ground. Again, I'm measuring a voltage, so it needs to be referenced to something. And now I'm going to take my blue wire, which is my channel 2 plus, and I'm going to connect that to the output. Okay, there we go. So now my channel 2 should be measuring the output of this device under test, this series diode clipper circuit. So let's go back over to the software view. And let's go ahead and turn on our channel 2. Okay. So what we are seeing over here is our input, which is that sine wave. You can see that we are clipping the negative portion of our waveform, so it is negative clipping circuit, as we would expect from a series diode clipper circuit. And if you look at the difference between our peak voltage and the peak of our output, it does look to be about the forward voltage drop of our diode. Okay, so that's correct. So everything that we would expect to see from our circuit, we are getting. Okay, and now there's a little bit of that question probably, which is what's up with this? I get the feeling that has to do with the sampling rate of our waveform. Let me see what happens if I turn up the amplitude just a little bit. So instead of 3 volts peak, let's do 5 volts peak. So I'll set this to 10. Okay, and let me try dropping the frequency. That looks like that made it worse. Let's go from 500 hertz. Let's take this to 60 hertz. And if you notice when I lowered the frequency, now it's not able to show an entire cycle on the oscilloscope. And in fact, it's having a hard time even triggering on it because of how slow it's going. Let me change that time base. There we go. Okay. And we are still seeing that clipping. What's going on? Now, as far as I understand this device to work, it should work with plus minus 10 volts on the input. So supposedly I shouldn't be violating the input voltage. So why are we clipping? And it got worse when I increased the voltage. So I'm fairly certain something here is clipping. It might actually be it's only happening when we're conducting. we're hitting the current limit of the bench of the function generator. I believe the function generator does not have a low enough impedance for the amount of current that I'm drawing. So let me go ahead and increase that resistance over there. I think that's what's going on. Okay, I am going to go from a 1K resistor to a 100K. This should make a pretty big difference in the current. Yep, that's the explanation of it. Okay, so yes, the impedance output of the function generator is not as low as personally I would like it to be, but it will work for our application. I know this because I already tested it. Okay, so that's how we can go ahead and use the function generator and oscilloscope. Now, as far as our project is concerned, okay, we're going to be using this for the first time on our amplifier circuit. And I've already actually set up this amplifier circuit. I placed it over here. Okay, so for the requirements of this amplifier lab that we're constructing, that BJT amplifier common emitter circuit, we're going to need a frequency of 1 kilohertz. So let's go ahead and let's do 1 kilohertz. I'm going to change my, let me go back to the software setup. Okay, let me go ahead. Never been a big fan of round knobs on software. And we're going to want a 500 millivolt peak signal for our project. That's what I spec'd out in the lab. So we're going to want a 1 volt peak to peak. Okay, again, I'm going to change the volts per division so we can see it. Now, if you notice, I can actually change the volts per division independently for my 2 channels. I can change the volts per division of channel 1. And I can also change it for, I want to keep the position at 0. And for channel 1, I want to change that to be, let's keep it the same right now. Okay, and let's go ahead, let's unplug our series diode clipper circuit from our device under test. And now what I'm going to do is, let's switch over to my board over here. My wires are a little short, so I'm going to have to stack this on top. My channel 1 output, my channel 1 input to the oscilloscope, I'm going to connect that to the output of my circuit, my common emitter amplifier circuit. And I'm going to go ahead and keep the grounds where they are. I'm going to take my channel 1 of my oscilloscope. I'm going to hook that up to the input of my circuit, and I'm going to take my function generator and I'm going to apply that there as well. Now, my common emitter amplifier circuit is running off of 15 volts. It is getting that 15 volts from the board. Sorry, from the MyDAQ through the red wire to the positive rail. And in this case, I'm using it up here. And so it's going through my wire all the way to the top and over here. And if you've noticed, I've constructed my circuit fairly cleanly, my common emitter amplifier circuit, and I've done it without using an excess of wires just to keep it clean. I try to use the component leads as much as possible. Cut down on problem areas and bad wires and things to that degree. Okay, so right now, let's go back to our oscilloscope. Check that out. Okay, so my channel 1 is set at 500 millivolts per division, and my channel 2 is set at 500 millivolts per division. Okay, I guess they're calling it channel 0 and channel 1. Why, when every other scope in the world uses channel 1 and channel 2? I don't know, but nevertheless, I will probably keep on making that mistake and calling it channel 1 and channel 2 as opposed to channel 0 and channel 1 because I've been using channel 1 and 2 for my entire life. Okay. I shouldn't say entire life, since I was a student. Okay, so what do we see here? Huh. All right. What's the first thing that we noticed about the output in blue and the input in yellow? Well, notice they're inverted. What's one of those features about a common emitter amplifier? The output is inverted from the input. So no surprise, my output is 180 degrees out of phase with my input. It is inverted. It should be. Okay. Now, what else do we notice about our channel 2 versus our channel 1, which is, well, the output is amplified. The voltage looks larger. And if you notice, I have these both set at the same volts per division. Now, when I'm making a relative comparison of voltage, make sure you keep channel 1 and channel 2 at the same scale. If I set this one at 1, now it looks like my channel 1, my input is larger than my output. It looks that way. However, again, you got to read the volts per division. My scale says 100 millivolts. So my input in yellow is going 1, 2, 3, 4, 500 millivolts peak, whereas my output is going 500, 1 volt, 1.5 volt, 2 volts, and about 2.4, 2.5 volts, somewhere around there. So make sure you put these at the same. Otherwise, you may think that you're not getting any amplification out of this, which is not true. We are amplifying. Our 500 millivolts is getting amplified up to whatever the top of this blue signal is at. Now, is there a way to measure this without having to count divisions? Now, if I'm just eyeballing this, I see we're at, let's see, 0 division. We're at 500, 1 volt, 1.5, 2, and we're under 2.5 volts. So I would call this 2.4 volts. That's just what I would call it. However, if I want to take a more precise measurement, I can use the cursor. So down here, there's a little box that says cursors. And I should be able to move these somehow. There we go. Look at that. Very cool. Okay, so I'm going to put this at the very top. Cursor 2 is going to be up here. And I'm going to put cursor 1 at the peak of channel 1. All right. You see, look at that. For the cursors, they call it C1 and C2. Whereas the channels they call channel 0, channel 1. You see, even the guys writing the code for this expected it to be 1 and 2. All right. Enough of me complaining. Let's look at what the output is. All right, we have 500 millivolts going in. If you look down here at C1, it says 500 millivolts. And if you look at the output of channel 2, it says 2.22 volts. Okay, so oh yeah, because each division is 500 millivolts. Half of one division would be 250 millivolts, and that's just under the halfway mark. So yes, 2.2 makes more sense. I was off in my previous statement when I said that that looked like 2.4 volts. It is 2.2. All right. So what else does this give us measurement of? Well, I mean, you can look also at the time between channel 1, the cursor 1 and the cursor 2, and that tells us over here, dt, the delta in time, it's 440 microseconds from one cursor to another. So you can use these cursors for taking all kinds of measurements, and I love having cursors on an oscilloscope, so I'm glad they're on here. Okay, so this is actually the output of the lab. This is what you should be getting. And I will go ahead and leave that there.